Good morning, students. My name is Mansuru Ade Okondeji. I'm from the Department of Electrical and Electronics Engineering Department, Bajo Polytechnic. We'll be teaching you Electric Circuit Theory 2. Electric Circuit Theory 2 has the following expected learning outcomes. 1. At the end of the module, students should master the following as the objectives. 1. Principle of power calculation in AC circuits should be well understood. 2. Students should understand three-phase systems and their applications. 3. Students should master and understand time domain analysis of RC, RL, and RLC series circuits, series and parallel. 4. Concept of magnetic coupling should be well understood. Now we start with power basics. Power, as we have known in an electric circuit, is the rate of flow of energy past a given point of the circuit. In an AC circuit, energy storage elements such as inductive and capacitive elements will result in periodic reversal of the direction of energy flow. The portion of power that average over a complete cycle of the AC waveform results in net transfer of energy in one direction is known as real power. There are portions of the power due to stored energy which returns the source to the source in each cycle, and this is known as reactive power. So reactive power are due to reactive elements, inductors and capacitor, while the real power is due to resistive elements, resistors. Now, if you look at this complex notation of the power system, here our S is equal to P plus JQ. We know that P here is the real part, which is the horizontal axis of this notation, and Q, which is the imaginary part, is the reactive part. So this S, which is the modulus of the complex power, now represents the apparent power. So to get the modulus of S here, we find square root of square of the two sum together, the real part and the imaginary part. So we know that our apparent power is absolute value of the complex power, which is P plus JQ. And from our elementary mathematics, we know if we are to find modulus or magnitude, we just find the square of this plus square of this, and then we take the roots for the sum. So it is worthy of note that all powers from our elementary science are measured in watts, but it is only the real power that we represent in watts in AC circuit. So reactive power has unit of VAR, capital VAR, which is voltage ampere reactive. Complex power or apparent power have unit of VA, which are voltage ampere simply put. Now, our real reactive and apparent power, to understand it a bit, we know that in a simple alternating circuit consisting of source and linear load, both the current and voltage are sinusoidal, that is, they are in pure sine waveform. If the load is purely resistive, the two quantities reverse their polarity at the same time. That's current and voltage reverse their polarity at the same time. So at every instant of the product of the voltage and current, you get positive value, indicating that the direction of energy flow does not reverse. In this case, only real power is transmitted or transferred. So for purely resistive load, we get true power. We can simply multiply current by voltage to get the true power in watts. If the load is, however, purely reactive, then the voltage and the current are 90 degrees out of phase. That's phase angle is 90 degrees. For half of each cycle, the product of the voltage and current is positive, but on the other half of the cycle, now when we have a sine wave, you have a part that is positive and then the part that is negative. So for the first part, you find the product of current and voltage, you get positive. For the other half, you get negative. So, and this will be equal in magnitude. So by the time you sum, what do you get? Zero. So invariably, power here is zero. So because we have said exactly as much energy flows towards the load as will also flow back, so there's no net energy flow over one cycle. In this case, only reactive energy flow. Then we say there's no net transfer of energy to the load. Practical loads, however, have all or most of these components, or the three. They have the three or sometimes two, but practical loads have resistance, inductance, and capacitance. So both real and reactive power will flow to the load. So power engineers measure apparent power as the vector sum of real and reactive power. So apparent power is the product of root mean square of voltage and current, simply IV, without considering the phase angle. So we get the apparent power as current times voltage. We care about apparent power because even though this current through it, that is current associated with reactive power, does not work at the load, does not useful work at the load. What it does is that it eats up the cable or wires, as the case may be, and this wastes energy. So conductors and transformers and generators must be sized to carry the total current, not just the current that does the useful work. So when you know the true power that your system will carry, you must also take care of the apparent power, because the apparent power will still eat up, the reactive power too will have effect. So we are mindful of the apparent power. So, and this involves the real and the reactive. We should as well note that if you see two apparent powers, you cannot add, just like you can add true power. If you have true power of 5 watt plus 3 watt, you simply say you have 8 watts. But if it is 5 VA plus 3 VA, you cannot add, because they have different displacement. The phasor angle between the current and the voltage might be different. So once they are different, you get different value. So it's only true power you can easily add. You cannot add apparent power except they have the same phasor angle, which will give them same power factor. If a capacitor and inductor are placed in parallel, then the current flowing through the inductor and the capacitor tend to cancel out rather than adding. Conventionally, capacitors are considered to generate reactive power and inductors to consume it. So assume capacitor generates reactive power and inductors consume it. This is the fundamental principle for controlling the power factor in electric power transmission system. Capacitors or inductors are inserted in a circuit to partially cancel out reactive power consumed by the load. So when you know the total capacitive power, you can know the total reactive power. So you try to cancel it out. So this will limit the power factor, This would improve the power factor. So we'll discuss this one later on. Well, as we have said, this complex power, absolute value of it is the length of this, and that is got by finding square root of p square plus q square, and this part represents the which is the imaginary power, represents the reactive power VAR, while this one represents the real part, watts, power in watts, which is the true power. So we have said reactive power does not transfer energy, so it is represented as imaginary on the vector diagram. Real power moves energy, so it is the real axis that is occupied. We have talked about the units: watts for real power, VA for apparent power, and VAR for reactive power. Understanding relationship between these is the art of power system, so we should understand the relationship. Since reactive power transfers no net energy to the load, it is sometimes called wattless power, but we know it has consequences being in a system, so we don't take it lightly. Now let's discuss the concept of power factor. Power factor, simply PF. You might see on the nameplate or a data sheet for an equipment. When you see PF, we know that stands for power factor, and we notice that this is usually having a value less than 1 for real load. So we know that this power factor, basically, if you consider this power triangle, we know this is reactive power, this is real power, and this is apparent power. So we know how to get the modulus of apparent power, which is square root of this square of this plus this square root of everything. But if we consider basic trigonometric ratio, we know that cos theta is adjacent over hypotenuse, so we can simply say adjacent, which is P over the adjacent cos theta is adjacent over hypotenuse, so that will be P over, what am I saying? So is P over Q, basically that's our power factor. And we say is a power factor is basically real power over reactive power in this case. And we should note okay, I think I'm correct. Power factor is basically real power over apparent power, so it's basically P over S, not P over Q as written here. So please do the correction, and that's why I'm a bit confused that it's against the basic principle of mathematics. So it's real power over apparent power, so it's actually P over S. You notice that I was a bit confused looking at when I was trying to say it's P over is adjacent over hypotenuse, while I'm saying Q here, but it's due to error during the preparation of the lecture notes. So the ratio of real power and apparent power in a circuit is called the power factor. Power factor is a measure of efficiency of power distribution system. It's a practical measure of this efficiency of a power distribution system. For two systems transmitting the same amount of real power, the system with the power factor will have higher circulating current due to energy that returns to the source from energy storage in the load. This higher current produce higher losses and reduce overall transmission efficiency. So a lower power factor circuit will have higher apparent power and higher losses for the same amount of real power. So the power factor is 1 when the voltage and current are in phase, that is for resistive load. That is when the voltage and current are in phase. But when you have a reactive load, they are 90 degrees out of phase for a purely inductive, purely capacitive. So when you now have all the three, you have a phase angle different from 90. It is 0 when the current leads or lag by 90 degrees. So that is when it's purely inductive or when it's purely capacitive. Power factor are usually stated as leading or lagging to show the sign of the phase angle, where the leading indicates a negative sign, a lagging indicates a positive sign. Purely capacitive circuit cause reactive power with the current waveform leading the voltage wave by 90 degrees, while purely inductive circuit cause the reactive power with the current waveform lagging the voltage waveform by 90 degrees. The result of this is that capacitive and inductive circuit elements tend to cancel out each other. Where the waveforms are purely sinusoidal, the power factor is cosine of the phase angle. As we are seeing here, power factor is the cosine of the angle between the current and the load, that's the displacement between the current and the load. So let's consider a simple example. Suppose we are given a complex power S as 5 plus J4. We notice that this is complex power S, which is also 5 plus J4, and we have said that the real part of this is a real power, while the imaginary is the reactive power. So complex power is given VA. To know the apparent power, we will find the square root of square of this plus square of this, which is 5 square 25 plus 16. So that's 49. Square root of 49, I'm sure you know the answer. We just decided to leave it this way, but we know we should simplify further. Real power here will just be the real part, which is 5 watts. The imaginary part here will be the reactive power, which is VAR. So power factor is real part over apparent. So I'm sure you know there's an error here too now. So which you should. So the answer here should not be for 4 over 5. You know what it should be, and you should try to implement based on the earlier error we tried to correct. So we should know that in power transmission and distribution, significant effort is made to control reactive power. This is typically done automatically by switching inductors or capacitor banks in and out, by adjusting generator excitation, and by other means. This shall be discussed later when we deal with how to correct power factors. And it is worthy of note that electricity distributing company most time produce meters which measure reactive power. This is to financially penalize customers with low power factor loads, because if they should use real power, by the time an owner uses a low power factor load, for instance, let's say your power is 100 watts, the real power you consume is you use apparent power of 100 VA. By the time you multiply by the phase angle, which is say 0.5, you'll be getting 50 watts. So that's what. But the waste that you cause will not be measured due to the reactive part of the load. So what is done is measure your apparent power. Then they will now multiply by their own distribution power factor, so this will make them not to lose. This is particularly relevant to customers operating highly inductive loads. Highly inductive loads. So please check your portal and be sure to do your assignments as posted there. Good day. God bless you.